in talking about projectile motion, we learned that, okay, anything that's in unpowered flight within the Earth's gravitational field is considered to be a projectile, right? And then we looked at a couple of different examples, okay? One of the examples was an object that is projected horizontally, okay? The other was just something falling. Anything just falling straight down is also a projectile, but that's pretty simple, okay? So this question here, I would like you to write down, okay, and give it a try. This is a horizontally projected projectile type question. All right, I want you guys to see if you remember how this works. I will give you a couple of little reminders. Okay? The biggest reminder that I can give you is that you need to break this up into the vertical parts and the horizontal parts. What's the one thing they share? Time. Okay? And you'll probably have to calculate that using one of them so you can use it for the other. Right? That's generally the way most projectile motion problems work. Okay? So at the beginning of this question, okay, this person runs off the cliff, horizontally off the cliff, at 8 meters per second. Obviously, they are going to do this, okay, and encounter the water. We're going to say there's water, so it's the less disastrous question. Okay, they hit the water 15 meters from the base of the cliff. Okay, those are the pieces of information that are outright given to us in the question. There are a couple of other ones that are hinted at. Okay, what are the other two that are hinted at? They're both vertical. Yep, gravity is one of them. Okay, our acceleration is 9.81 meters per second squared, downwards. And what's the other piece of vertical information? VI is 0. That is the key to this question, is remembering that vertically speaking, running horizontally off a cliff, okay, is an initial vertical velocity 0. Okay. So that's your givens. See if you can figure out the height of the cliff. So what I have to remember here is that the time is shared by both the horizontal and vertical components of this movement. Okay. The other thing I have to remember is that horizontally, the object travels at uniform velocity, right? Its velocity, horizontal velocity of 8 meters per second does not change. There's nothing to speed it up or slow it down. Okay, so what we're looking at is that we can use v equals d over t to find the time using the horizontal information. So we're going to have our 15 meters divided by 8 meters per second, okay, and that's going to give us our total time of the fall. Okay, so we'll have 15 divided by 8. Right, so we're looking at 1.875 seconds. Okay, that can come over here and be an additional piece of information for the height, for finding the height of the cliff. Can I now find the height of the cliff? Yes, because now I'm looking for d, the vertical distance, okay, of the height of the cliff, and I have a, vi, and t to do it with, okay, which is why I would then use this formula. Okay, since VI is 0, okay, and this is the formula I'm using, VI times T plus 1/2 AT squared. Since VI is 0, I just plug in 1/2 AT squared, and I get that the height of the cliff is 17 meters. Right? Yesterday, we did one like this. I gave you the height of the cliff, and I asked you to find how far it traveled horizontally, how far from the base of the cliff. The only other way to ask you one of these would be to give you a different set of information and ask you to find out what speed they ran off the cliff at. Okay? In the end, it's pretty much the same set of steps. I got to find time. I got to use the time over here to find the speed. Okay? But in actual fact, you're usually finding the time because that's the one thing they both share.
Isn't the 17 the displacement of the jump, like the diagonal?
No, it's not this.
It's not.
No, because there's no acceleration along this plane.
Oh,
right? It's a
yeah.
vertical acceleration.
Okay.
I used all vertical information, so I found this height here. Okay? Because they didn't actually do this,
Yeah.
right? They did this. Yeah, you're right. Their true displacement would be this, but their vertical displacement is 17 meters.
Yeah, that makes sense.
All right, so that's the first type. Okay, that's the type we talked about yesterday, a horizontally projected projectile. Then I showed you the mega whoosh thing, okay, where the guy shot off the end of the ramp and landed in the little kiddie pool. Okay, so what we want to look at in terms of how those questions work, okay, is that they are similar in that, again, time is shared by both the horizontal and vertical parts. The horizontal velocity never changes, okay, but what's different is we're projected not horizontally, but at an angle. Right? So we have to calculate our initial vertical velocity and our horizontal velocity a little bit differently. Okay? So what we have, okay, in a situation like this is we would probably be given the velocity at which the projectile is being launched. All right? So we'd have, let's say, a launching speed of 25 meters per second. And we'll say that that is 30 degrees above the horizontal. Okay, so I've launched this thing or thrown it or whatever I've done to put it in the air. Okay, at 25 meters per second, 30 degrees above the horizontal. Okay, now obviously what's going to happen is that projectile is going to follow an arc that is going to re-encounter the ground some distance away, just like when you played with the hose as a kid. Okay? So a question like this would probably ask me two different things. It would give me this information and just this information and ask me to calculate how far it'll travel horizontally and what the maximum height of the projectile will be. Okay, so it's going to ask me to calculate two things and give me one. Okay, now does it actually give me more than one piece of information? It does. Okay, but again, I want to break this up into vertical parts and horizontal parts. Okay, I have a piece of information vertically that I know right now. What is it? Right, the acceleration is 9.81, but it's negative this time. Okay, why am I making it negative this time?
Because you threw the object up and gravity is forcing it.
Right. Okay, from a vertical perspective, this object is going to change direction. It starts moving up and ends moving down. All right, so I have to represent those with positives and negatives. All right, so I know this number right off the bat. Here's the other thing that you're going to know right after I teach it to you. Okay, and that is that this vector has a horizontal component and a vertical component. Okay, the horizontal component, okay, if I calculate x, x is a velocity. It's the horizontal component of this 25 meters per second. It is how fast the object is traveling horizontally. Everyone okay with that? Okay, then it's going to go over here as that constant horizontal velocity, okay, that the object will have throughout its flight. How will I calculate this side?
Using cosine law.
Right. Well, not using cosine law, but using cos. Yes. Okay. So I'm going to find the x component or the horizontal component here, okay, by doing vector components. Okay, solving for my vector components. That's going to mean the cos of 30 degrees times 25 meters per second. Okay, so this thing is moving at 21.651 meters per second. Horizontal. Okay. The other thing I need to know is that this side of the triangle is its vertical component. It is how fast the object is moving vertically at the time of launch. Why do I add the time of launch on when I didn't do that for the horizontal part?
Because the object still goes up after you launch it.
Right, it still goes up. Its velocity is going to, well, actually it's going to decrease. It's going to start slowing down right away, okay, because gravity is going to start pulling it down. It's going to accelerate is basically what I'm getting at. Okay? From a vertical perspective, the object is undergoing accelerated motion. I can't just say V vertical. V vertical changes all the time. V horizontal is constant. Okay? So if I solve for this side, I'll know the initial vertical velocity. Okay? So that'll be the sine of 30 times 25, which will be 12.5. Positive. 12.5 meters per second. Okay? So when this thing is launched, it's launched at 25 meters per second, 30 degrees above the horizontal. That means it's moving at 12.5 meters per second upwards and 21.651 meters per second horizontally. The 21.651 will be constant, but the vertical will change. Okay? All right. So when this thing is launched, and it's actually launched from here, okay, it's going to travel through this arc, and then it's going to hit the ground over here. The ground is level, so it goes all the way up and all the way back down. Same height up, same height down. Okay? So, in the perfect physical world, where there's no air resistance or anything else to mess this up, how fast is it going when it comes back to the ground? What is it?
Oh, should negative 9.81.
No, it's going to accelerate at negative 9.81 meters per second squared. How fast is it going to be going after it goes up and then comes back down to here?
Well, once it hits the ground, it's going to be 0, but going down would be terminal velocity if it's
Okay, but again, perfect physical world, no air. So no terminal velocity.
oh, so no terminal velocity.
Okay, I want you to watch what this thing looks like from a vertical perspective. Same speed. Okay, when it comes back down to the same height it was launched from, okay, so it's launched at 12.5. It goes up and it's accelerating at 9.81 meters per second squared down. It slows, it reaches a speed of 0 at its maximum height. And then it accelerates at the exact same rate over the exact same distance back down to the ground, which means it has to be going the same speed it left at because everything else is the same. Okay? So an object that's launched at an angle, okay, will have the same vertical initial and vertical final velocities, provided it's on a level surface. Okay? As long as that d is the same, okay, it's going to be the same number when it comes back down. Right? Everybody okay with that idea? Yes? Okay. So that means then that VF will be negative 12.5 meters per second. All right. Now we said the question wanted us to calculate two things. How far it would go horizontally and how far it would go, or what its maximum height would be. All right. Let's do the horizontal distance first. So I'm looking for the horizontal distance. What do I need? Right.
Velocity and time.
Right, I need velocity and time. Velocity I have, time I don't. Can I find the time? Yeah, because I have A, VI, and VF from the vertical part. Okay, so I can solve for the time using the vertical information and then bring it over to the horizontal part. So T will equal VF minus VI over A. So that'll be negative 12.5 minus 12.5 over negative 9.81. Okay, so that'll be negative 25 divided by negative 9.81. All right, so this thing is going to be in the air for 2.55 seconds. Okay, the entire 2.55 seconds, it is traveling horizontally at 21.651 meters per second. Can I calculate D now? Yeah. Okay. D will equal V times T. Right? So that's our 21.651 times our 2.55. Okay. Now obviously we're not going to round off. We're going to use all the big numbers from here. So times 21.650,63509. Okay, so it's going to travel 55 meters horizontally. Okay, is that a long way to throw something? Yeah, 55 meters is a long way to throw something. And you got pretty good arm. Okay, if you're throwing something of any mass, 55 meters. All right, that's one of the things they wanted me to calculate. The other thing they wanted me to calculate was the maximum height the projectile would reach. Okay, so that occurs here at the halfway point of the flight. Okay, everybody all right with that? Okay, so what I'm looking for is a vertical displacement at this point in the flight. Okay, I already know what VI is. Okay, that didn't change. I already know what acceleration is. I'm looking for displacement. Okay, I need one of two pieces of information if I'm going to do this. I either need the speed, or the velocity, sorry, at this point, or I need the time at this point, one or the other. Okay, everybody with me there? Right? If I'm looking for D, okay, I need A, VI, and T, or I need A, VI, and VF. Okay, one or the other. Right? Now, the time I calculated here was for how much of the flight? For the whole thing. Where does this occur? Halfway. Okay, so I could divide my time in half and calculate what my displacement is, or I can save myself a little bit of math. How fast is the object going at its maximum height? 0. Okay, I've got VF, I've got VI, I've got A. Can I find D? Okay, that formula will get D from the information I have. Okay, so I'm just going to manipulate for D, VF squared minus VI squared over 2 times A. So that'll be 0 squared minus 12.5 squared divided by 2 times 9.81. So all right. This is going to reach a height of 8.0 meters. Okay, everybody all right with that? Now, like we said, we could also use half the time, and I'll get the same number. Okay, if I use half the time, okay, I'm going to use this formula here: D equals VI times T plus 1/2 AT squared. Okay, that will get me D as well. Okay. So I'll have 12.5 times half of 2.55, so 1.225. Okay, plus 1/2 times 9.81 times 1.225 squared. Okay, so 12.5. Okay, still get 8 meters per second. I get slightly different because I rounded the numbers off. Okay, but still get 8.0 meters per second, or sorry, meters as my displacement. Okay, now, for me, whenever I encounter one of these and I'm looking for maximum height, I use this formula. I never do it this way. It's up to you which way you do it. They'll both give you the right answer. They'll give you exactly the same answer. But here's what happens. People forget to divide the time in half. Like 75% of the time when they do it that way. Forget to divide the time in half. And then get a ridiculous number. Okay? So it's up to you. But if you're going to use the time one, make sure you use half. Okay, so that's a projectile projected at an angle. Okay, all projectiles follow this same arc. Okay, so all projectiles follow this same arc. Okay, in the perfect physical world. In the real world, the back end of that arc becomes a little flatter due to air resistance. Okay, so a true projectile arc actually looks something like this. Okay, it's a little flatter at the end because of air resistance slowing down the horizontal velocity a little bit. Okay, now I'm going to show you. We're going to look at a couple videos of really bad movie projectile motion physics. Because movie physics is different from real physics. Right? So I'm going to show you a couple here. So in that particular jump over the river, okay, we know that the General Lee is moving at 32 meters per second. That's around 120 kilometers an hour. Okay, the ramp is angled at 20 degrees above the horizontal. And we want to find the distance across the river and the maximum height of the General Lee as it flies across. So the same two things we calculated in the example just a minute ago are what we have to calculate here. So you can start off with this diagram. Okay, our projected velocity is 32 meters per second, 20 degrees above the horizontal. Obviously the General Lee flies through a projectile arc that encounters the ground at the same height on the other side of the river. Okay. You need your vertical and your horizontal pieces of information. Okay? And you can start off with this one. Okay, give you a couple minutes to see how you do. All right, so with any projectile motion question, like we said, we want to keep our horizontal and vertical pieces of information separate. Okay, since this is a velocity vector, the 32 meters per second, it will have a horizontal component that will represent the constant horizontal velocity. Okay, that will be calculated by going cos of 20 times 32. Cos of 20 times 32. Okay, our constant horizontal velocity is 30.07 meters per second. Okay, the other thing we have to remember is that this also has a vertical component and that will represent the initial vertical velocity. Okay, so VI is the opposite side of that triangle, so that'll be the sine of 20 times 32. All right, so we're looking at 10.94 meters per second upwards. All right, what's the other thing I have to remember about the General Lee since it takes off and lands at the same height?
Final velocity.
Final velocity is?
Negative 10.94 meters.
Right, it's the opposite of the initial, so negative 10.94 meters per second. All right, so now I've calculated, okay, basically my givens, right, for this problem. If I want to calculate how far this object travels horizontally, okay, I am going to need V and T. I already have V, right? I'm going to have to calculate time, and I'm going to have to calculate it using my vertical information. Time will equal VF minus VI over A. Okay, so that'll be negative 10.94 minus 10.94 divided by negative 9.81. Right, so when I do that, basically I'm just going to take this number and multiply it by 2, okay, and then divide it by 9.81. All right, so this thing is going to be in the air for 2.23 seconds. Okay, which is a long time to be in a car flying through the air over a river. Okay? All right, so we're going to bring that time over here because as long as it's in the air, it's moving both vertically and horizontally. Right? So D will equal 30.07 times our 2.23. All right, so horizontally, the General Lee is going to travel 67 meters. All right, to give you an idea, that is 2/3 of one of the straightaways on the running track out back. Okay, it's 2/3 of one side of the running track, right? It's more, well, it's almost 3/4 of the football field, okay, from one end zone to the other, right? It's big, okay? So 67 meters. All right, that's the first thing they wanted us to calculate. The other thing they want us to calculate is what's the maximum height of the general lead. Okay, so we need to know its vertical displacement here when its speed is 0, right? When its vertical velocity is 0 meters per second, we're looking for d. Okay, so I'm going to use this formula here, vf squared equals vi squared, because I have that, plus 2a, I have that, okay, equals d, that's what I'm looking for, right? So d will equal vf squared minus vi squared over 2a, so that'll be 0 minus 10.94 squared divided by 2 times negative 9.81. Okay, so okay, so I'm taking that number squared and I'm dividing it by 19.62. I'm not making either one negative because they're both negative, and I'll get a positive either way. Okay? All right, so this thing is going to reach a maximum height of 6.10, well actually 6.1, we only have 2 significant figures here, 6.1 meters. Okay, that's roughly the equivalent of dropping it off the top of the gym. Okay, that wouldn't end well for a car to be dropped that far. Okay, so basically all projectile motion problems are going to work similar. Okay, they might not always ask for the horizontal distance. Sometimes they might give you the horizontal distance and ask you to calculate the projected velocity. It's just some working backwards, but we'll go over lots of examples like that. Okay, now I'm going to show you an example of absolutely terrible movie physics. Okay, absolutely terrible.